All right, section 3.2 and 3.3, 3.4, and 3.5 are going to take our 4 basic operations for whole numbers and talk about each of them independently. So in this section, we're specifically going to be looking at addition. We're going to be looking at models for addition. We're going to be looking at algorithms, which means ways of doing addition. And I'm pretty sure you're going to learn something you didn't know before, because there's a lot of models out there and they're not always taught at every school. The kicker with what we're doing in this is to help you to understand a couple of things. Maybe I should back up just a second. 3.1 is not something that you're probably going to teach. Okay, you're not going to do division scaffolding probably. You might end up with some, gifted and talented program where they look at some cool stuff like that, and that'd be great. But that's probably not the content that you're looking at. The point of 3.1 is to give you a historical perspective of where he came from, why our number system is better than ones in the past, really. And also, as we're working on the other bases, to give you some sort of a sense of how confusing a base 10 number system that you're super familiar with and feel like is so easy cannot feel so super easy and familiar with kids when they first encounter it. That's the point of 3.1. When we're looking in 3.2, 3.3, and 3.4, and 3.5, you're going to be looking for several things. You're going to be looking for ways of teaching, different ways of explaining. You're also going to be looking and thinking about the fact that the curriculum that you're assigned to use in your school may use one or more of these methods. And I'd kind of like for you to see that there's other methods out there before you leave OBU. Does that make sense? Okay, so we're starting out in 3.2 with just an addition definition. We're going to let A and B be 2 disjoint finite sets. If the number of items in set A is A, the number of items in set B is B, then if we add A and B together, it's the same thing as counting the union of A and the union of B. Those numbers A and B are called the addends, and A plus B is called the sum. Okay, so let's talk about that word disjoint, because our first question deals with that. Disjoint means that they don't overlap. So if we were to draw a Venn diagram of them, they would be 2 non-overlapping circles. That's disjoint. So anytime we drew our Venn diagrams before where they overlapped, those were disjoint sets. They had something in common. So we're going to talk about in example 1 why that phrase disjoint, that word disjoint, matters. Who cares? What if they aren't disjoint? What would happen? So that's exactly what it asks you to do. It says to give an example to show why you have to have things that are disjoint. So what we're going to do is we're going to create a set A and a set B where they have something that makes them not disjoint, i.e. they overlap one another. So I'm going to call set A, I'm going to make set A equal to the set 1, 2, 3, 4. And we're going to make set B 3, 4, 5, 6, 7. There's nothing special about these sets. The only thing that matters as I create them is that they overlap. And these do overlap. Where do they overlap? 3 and 4. You got it. Good job. So what we're going to do is a counting argument. We're going to count how many things are in set A. What's the cardinality of set A? 4. What's the cardinality of set B? 5. Now let's come down here for a moment and we're going to create the union. What is the union of the set 1, 2, 3, 4 with the set 3, 4, 5, 6, 7? Union means all the things that are in both of the sets, but we don't rewrite numbers. Okay. Does that make sense? How many items are there in the union? 7. And what we want to notice is that when we add these together, we do not get 7. In particular, we get 2 more than 7. Why? The two numbers that are overlapped, we counted them twice. We counted them when we counted set A, and we counted them when we counted set B. So that's why that part of the definition matters. Now, what I want to look at next is two models, for addition. One of the things that's cool about looking at models is that as you work with kids, you might find that absolutely know how to concretely just add numbers. If I give them two numbers together, they can add them. But when you put them into a word problem, barriers go up, and they don't know what to do. That probably happens to some of you. If I take the same content and I put it into a word problem, you kind of go, oh my goodness, now there's words that are going on here, and I'm not quite sure what it's asking me to do. Well, the interesting things about models are if you can identify that a student always struggles when a problem looks like this, that gives you information about how to help that student. Whereas if you just think that sometimes they miss it and sometimes they get it right, it makes it really difficult to know why they're missing problems. So we're going to take a look at models for addition, subtraction, multiplication, and division with that in mind, that our goal is to try to help kids to figure out what it is about the type of problems they're looking at that might be causing them problems. So the first model for addition is called the set model, and it's typically used for whole objects. For example, Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? And we can actually do this in a very concrete way. This is a visual that will work very nicely. What color did I start with? Blue. And we can draw. She has 3 blue crayons. And the cool thing is we don't even have to make them all the same size because you know crayons aren't, right? Kids use them, they mush down, they're still usable, right? And then I have 2 red crayons. And the question is how many crayons in total, altogether, whatever, do I have? And the answer is, that's a terrible 5. Let's try that again. 5 crayons. This is a set model. It doesn't matter how big the crayon is, it's still called a crayon, right? When the kids break the crayons in half, it's still called a crayon. Well, the other model actually has something where it matters how big the object is. This is a number line or a measurement model. And it's typically used for objects, even when you're talking about whole numbers, it's still objects that can be partitioned. For example, Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building material does Joe have? Okay, so I'm not using decimals or fractions or anything. That's another chapter, right? But this is still an object that you could break apart and you wouldn't call it the same thing. Are you with me? I break the crayon into 2/3 and 1/3, I still call it a crayon. And I probably call each piece a crayon at that point, which is a little weird, right? But here, if I start breaking things apart, the length of it changes and it doesn't make the same sense. So on this one, you can actually count it or think about it from a number line or a measurement perspective. So I start with 0. 1, 2, 3, 4, 5, 6, 7. Okay, and this is just extending it here. I can still draw a visual of what's going on. This one is 4 feet of wood. So here's my 1, 2, 3, 4, pretend like they were drawn better, but there's 4 feet of wood. I can put them end to end. And then I've got my 3 feet of aluminum. 1, 2, and 3. And I can still count the objects in much the same way, but I can also count the distances that the objects have crossed or passed through. And the answer then would be 7 feet. So it's not quite the same thing, right? I didn't count the lengths of the crayons, I just counted the objects. Here, I'm not really counting objects, I'm really more looking at their length. Some language that we see used frequently when we do comparisons of values is a phrase called less than. So less than and greater than. Greater than is talked about in your homework, but less than we'll talk about here. For any whole numbers a and b, is less than b is written a, and of course the symbol less than b, if and only if there exists a natural number k such that a plus k is equal to b. Okay, for example, the reason we would say that 3 is less than 5 is because 3 plus 2 is equal to 5. There's a number that I can put in here, a whole number, that sort of makes up the space that they are apart. That's what it means to be less than, is if I added something to it, it could be equal to it. Equivalently, we could talk about the word less than or the phrase less than, but do it from a perspective of subtraction instead of from this perspective of addition. So if we did this from the perspective of subtraction, most of what is said in that definition would stay the same. It would start out for any whole numbers a and b, a is less than b. All of the first line into the second would stay the same. So let's just write that part down first. And it's still got the same notation written, a less than b. Okay, so all of this stays the same. Half the definition is identical. The difference has to come in down here. How can I write this statement, this equation, to use subtraction instead of to use addition and to relate a and b together? Right. So I'm going to leave the a and the b in the same sides they are, but I'm going to write it like you just said. B minus k on one side and a on the other side. Right? So instead of adding something to a to make them equal, I'm taking something away from b to make them equal. So I can structure all the things again. I mean, everything else is the same except this piece right here. So this is if and only if there exists a natural number k such that a is equal to b minus k. Right? Johnny has 3 cookies and Joe has 4 cookies. You could either give an extra cookie to Johnny or you could take a cookie away from Joe and then they'd have the same amount. All right, we're going to talk about properties of numbers. There are properties of numbers that exist only for certain types of numbers. So you don't have all of these properties all the time, and I'll give you examples of that as we see them occur. The first property is called the closure property, and it's the property that people seem to have the most difficulty really grasping or feeling like that they've grasped it. The closure property simply says that if you have a whole number and you add a whole number, you get another whole number. Right? So when kids have actually learned how to count from 0 to 100 or whatever, it doesn't matter what 2 numbers you pick for them, they're always getting a number that they're familiar with. You can't add 4 plus 7 and get something that's a fraction or a negative. Right? None of that happens. Now, that's very specific to addition, and it's very specific to whole numbers. Because if you think about something that really looks fractional, right, like 1/2. If you add 1/2 and 1/2, it looks like a whole number when you're done, 1, right? Like, yeah, it has the version of 2 over 2, but for some reason it doesn't quite feel the same. Definitely true for this being an addition fact. If you do this the other direction, right, 3 minus 7. 3 minus 7 is not a whole number. 3 plus 7 is. We're good to go. 3 minus 7 is not. So it's very specific to this operation. It's an addition operation. It doesn't work for subtraction. I've described it this way before too. I'll try this one. Closure is the idea for whatever set you're working with. In this case, we're talking about whole numbers. But we could be talking about even numbers. So let's just play with even numbers for a moment. Is it true that if I add an even number plus an even number, I get another even number?
Yes.
Yes. Does it work for odds?
3 plus 7 equals 10.
So no. Odd plus odd doesn't equal odd, right?
Yeah.
Okay. So let's think and imagine the evens versus odds for the moment. Let's say I have all the even numbers in this room with us. They're floating around in the air. You can pluck them out of the air at will. You can even pluck out 2 2s. That's okay, right? Like a number can be duplicated floating around in here. All even numbers. If I can take 2 even numbers or 2 whole numbers or 2 odd numbers or whatever's floating around in here, and I add them together and that type of number is still in my room, it's called a closed set because the door's closed and I don't have to go outside the room to get another value. So it doesn't work with odd numbers. If I take an odd number 3 and an odd number 7, and if I add 3 plus 7 together, I get a 10, and it's only odd numbers in the room, I'd have to open the door, hence it would not be a closed set to go find the number 10.
Gotta go to the community.
Yeah, gotta go out the door. Okay, so that's closure. The commutative property is the idea that the order of your addition doesn't matter. Right? 3 plus 5 is 5 plus 3. It's a fantastic fact. If your kids understand that, it makes addition so much easier because once you get to bigger number addition with smallers, right, like 9 plus 2, well, they already know it because they already did 2 plus 9, right? It makes addition so much easier because the order doesn't matter. Is this true for subtraction?
No.
Nope. It's this very special property for addition. Our next property is the associative property. The associative property is super cool too. It says that I can group sets of numbers together in different orders to do the addition. So I don't necessarily have to really worry about the parentheses. A plus B plus C would be the same thing if I added the B and the C together first and then the A next. And that regrouping feature is super friendly because sometimes it's easier to add certain numbers together. Right? 3 plus 7 is 10. That's much nicer than adding 3 plus 8. So if I had the ability within a string of numbers to add things together where pieces added up to 10, that'd be really nice to do. And I do have that ability. The last property is called the identity property. And specifically, I want you to write this in here. It's understood, but we'll need to know and focus on this later. This is the additive identity. Right? We will be encountering another identity later. The additive identity element is the number 0. Because 0 plus anything and anything plus 0 both keep the number anything the same. A plus 0 and 0 plus A are both equal to A. Okay, so I'm going to finish up with example 3, and then you guys are going to get into groups. So example 3 asks us to identify which property is being used. Did I go too fast?
Yeah.
Sorry. All right, so taking a look, properties, we're identifying which of those 4 properties we see used on each of these examples. What property do you see used on part A? That is the commutative property. Right? 8 plus 6 and 6 plus 8 reversed. How about B? Not associative. It's really tempting because I see parentheses. It's something else. It's the identity property. Do you see that there's a 0 on the left and not a 0 on the right? That's the identity property, actually. So this is and it's the additive, so please use the word additive identity. How about C? Be careful, just because there's parentheses, just like we saw in B, does not mean that it's associative. What's actually happening on C? It's the commutative. The numbers that are inside the set of parentheses do not change. They just change the order that they're in. And changing order is a commutative property. And it is commutative. I have people misspell that particular word all the time. You get all sorts of interesting things. Communicative. Yeah, I got some interesting ones for that one. How about D? That one's associative. So the numbers that are in the set, like the 532 is the same. The order is the same, 532, 532. But what's inside the parentheses changes. This one's 5 plus 3, and this one's 3 plus 2. So that is actually the associative property. That's associative. All right, we will finish section 3.2 on Monday.